तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
The question is, how do you find the equation of a phase trajectory in phase space from the Hamilton equations? And his question is, there are two such equations. So in general you have a thing like q dot is delta h over delta p and p dot is minus delta h over delta q, and the question is, how do you find the equation to the phase trajectory in n dimensional, 2n dimensional phase space? Of course you have to solve these equations before you can do that, and as I said, that is not always easy to do. Numerically you can integrate this set of equations, but then if it is not an integrable system, then you can't write explicit solutions in general. But if it is a 1 degree of freedom system, in other words the phase space is 2 dimensional, then there is just a phase plane, and then of course we know the equations of motion. They are simply given by h of qp equal to constant. That gives you the trajectory in the QP space, in the QP plane, some trajectory of this kind from a single constant of the motion. The moment you have more degrees of freedom, then of course you can't do this, you need more constants of the motion, and then the question of integrability comes in. But in a 1 degree of freedom system, finding the phase trajectory is quite trivial for an autonomous Hamiltonian. It's just h of qp equal to constant, and that's it. Now of course as soon as you have more degrees of freedom, not only do you need n constants in involution with each other, but then you should also be able to find the canonical transformation which would take you to action angle variables and then solve the problem, which is not always easy to do. But what we are going to do now is to start from this point and ask what can happen in general, because the number of solvable problems, the number of integrable problems is quite small, is quite restricted, especially if the degrees of freedom are interacting with each other. If they are decoupled, of course, then it becomes a trivial problem. So what does one do in general? Well, the important thing is to ask what is the qualitative behavior of phase trajectories in phase space, and now I would like to show you that there is in fact a kind of hierarchy of randomness, and this will take us on to chaos. The situation is as follows. In the simplest instance you have integrable systems. This would mean of course the motion is regular and you can find the constants of the motion, you can write the solutions down for all the dynamical variables explicitly as functions of time, and for arbitrarily long times you can predict what the future is going to do given initial conditions. This would be the small set of integrable systems, of which the harmonic oscillator, the Kepler problem and so on, the central force problem, these are all examples. Next in complexity, well, among integrable systems itself we are restricting ourselves to bounded motion, not motion in infinite phase space but bounded motion, generally periodic motion of some kind. Then the simplest of such motion is of course such kinds of motion is periodic motion. A little more complicated than periodic motion is quasi-periodic motion, where you have several periods in the problem but they are not commensurate with each other. So the next in increasing complexity is quasi-periodic motion. The next step in this increasing order of complexity is when the motion is not even quasi-periodic but it is ergodic, in the sense that a set of initial conditions comes arbitrarily close to every point in phase space as given sufficient time. So the next one is ergodic motion. Quasi-periodic motion is ergodic on a torus, of some kind. We saw that the torus gets densely filled and so on, but you could have something which is simply ergodic on what? On what sort of phase space? Well, if it is a Hamiltonian system, then we know the Hamiltonian is a constant of the motion, and if you do not have other constants of the motion which are analytic functions, then this system in general, the motion would be ergodic on the energy surface. So if you have 1 or 2 or 3 constants of the motion, then an arbitrary set of initial conditions, initial volume element in phase space, could visit all regions of phase space given sufficient time. So for example, if this, just to illustrate, if this board is your phase space and I start with a set of initial conditions here, each of these points goes into a trajectory, is part of a trajectory. After some time this set of initial conditions could be there, and after some time it could be here, and so on and so on. Does not have to come right back to its starting point, because then it would become periodic motion. So if the motion is such that an initial set of initial conditions, an initial volume element in phase space visits the neighborhood of every point of some part of phase space given sufficient time, then we say the motion is ergodic on that part of phase space, in general perhaps the surface of constant energy or something like that. So this is the next step in complexity, ergodic. It is not periodic, it is not quasi periodic, it could be worse, it could be ergodic in this motion. But now you could ask, well, if I put a drop of ink in a beaker of water and I now look at motion not in phase space but in real physical space, I look at this ink which is a dye, is this ergodic in the sense that you put this in the beaker, that is your full space, is this motion going to be ergodic in some sense? You wait long enough and you realize that this piece of little drop of ink actually puts out tendrils, becomes very complicated, we assume no chemical reactions, and eventually it gets completely mixed up with the whole of the phase space, with the whole of the space that is available to it. So in that sense, if I start with, in this beaker of water, if I start with a drop of ink, after some time this does that and then it does that and so on. So you see portions of this initial ink, this initial volume element, are to be found arbitrarily close to every point in the available space, and in this sense it is ergodic, because given enough time there are little pieces or bits of ink, little molecules which come from the initial volume element, and arbitrarily close to every portion of this volume you can actually find some parts of the initial ink drop. In that sense it is ergodic, but it is worse than that. What is actually happening is that as time goes on, an initial volume element could become distorted. Even if the measure is preserved, even if the volume is preserved, as in the case of Hamiltonian flows. In the case of dissipative flows, of course the volume itself could shrink, but the point is that it could in this case actually have a distortion, a very bad distortion in shape. And a little later it might do this. Even if this initial volume is equal to this final volume here, you can see that pieces of this initial volume are getting separated out, and this could go on and on and on, and in fact it could end up such that pieces of this initial thing would be arbitrarily far apart as the system size itself as time goes on. Such motion is of course ergodic, because little pieces of this go through everywhere, but it is more than that. This thing has got mixed up with the rest of the phase space completely. So what would you call such motion? Mixing. It is called mixing. This kind of motion is called mixing, and that is the next step. We need to make this concept of mixing a little more precise, and let me do that in a little formal way. Although there are many definitions of mixing, you have to ask mixing in what sense? How do I define distance between 2 points in phase space and so on? So we can make this more precise. Strong mixing is the following. Suppose we have a phase space, and let us call the volume of this phase space omega, this full phase space, okay. Let us call that omega, the full set of points in phase space, and let us take a small initial set here and let me call this A. So the set of points that belong to this volume element I call A, the full space I call omega, all the points of the phase space I call omega. After some time this A, if this is A0 at time 0, at the end of one time step this set of initial points has moved out and perhaps become something like this, and let us call this A1. So all these points are moved into that, and a little later perhaps they have become this, and that is A2 and so on. Now let me put a window here, a reference volume, and call it B. If the whole thing is stirred up completely and points of this A after n time steps are completely mixed up, then how much of A0 would be sitting inside B? How much of this would be sitting here? Exactly, as much would sit there as is the initial concentration, right. So what would you say is the measure? Let us put measures here. I would like to know what is the measure of A intersection B. After n time steps, A sub n is the set of points which started off as A naught, and I ask what is the measure of the intersection of the set A n with B? How much of A n is sitting inside intersects with B, is common to B? So what would that be? Well, the intersection of that to A naught, the ratio of this intersection to how much you started with, if this is equal to mu of B over mu of omega itself, right, it tells you how big the window you have compared to the entire volume. If this is true in the limit in which n goes to infinity, then I would say it is completely mixed totally. So if limit n tends to infinity mu of A intersection B is equal to by mu I mean the volume or the measure, whatever you would like to call it. The reason I introduce a mu will become clear a little later when we do statistical physics. Then the dynamics is said to be strongly mixing. The intuitive idea is very clear. If I mix a little bit on, the famous example is ink in water, or better still rum and cola. So you have a lot of cola and you put in a little bit of rum and you stir it thoroughly, then if the amount of cola, the amount of rum that you have in any reference volume satisfies this ratio, then you would say it has been completely mixed up. So in that sense, strong mixing is a very familiar property in dynamical systems, and it goes one step beyond ergodicity. I would like you to appreciate the fact that mixing implies ergodicity, but ergodicity does not imply mixing, because you could have ergodicity without distortion of the volume elements, whereas mixing implies certainly that it distorts badly. So the implication is in one direction. Mixing implies ergodicity, the converse is not necessarily true. Now when you take a liquid and stir two liquids into each other, then you are actually helping the mixing process. And the next question to ask is how fast does it mix, how rapidly does it mix, because that is crucial. If it mixes so slowly that it takes the age of the universe to get thoroughly mixed up, then it is for all practical purposes not mixing at all. So the question is how fast does it do it. If I take this familiar example of a drop of ink in water, how fast do you think it mixes? So I take a little piece of dye here, and then of course it will start putting out tendrils, and by molecular diffusion it gradually the concentration equalizes everywhere. How fast do you think that is happening? It has to do with what is the rate at which this increases. In other words, what is the rate at which these points separate out. So mind you, a point which started here has ended up there, and a point which started here might have ended up here, and the question is how fast is this separating. So now we are getting quantitative, we would like to know how fast is this happening, and we would like to know the rate at which it is happening. Of course it would depend on where you are, what the dynamics is, what the system is, and so on, but what would you say is the case here in the case of ink? Pardon me? Yeah, so I am asking on the average. Of course you know that this tendril is highly irregular, it is not a regular process at all. So what starts out as a nice little drop soon puts out all these filaments and so on. So we are asking on the average how does it separate, how rapidly does it separate, and this is happening due to diffusion. It could take a long time, you can see these beautiful patterns for a long time, so it is obviously a slow process, and it is a complicated answer. If you heat this liquid and there are thermal currents, then of course convection currents would be set up, and that would mix things fairly fast. You put a spoon in it and you stir it, that makes it even faster. But suppose you do not want to stir the the sugar in your coffee, but you would like to have this mix very slowly, perhaps because you would like to enjoy company for a little longer, depends on the company of course. Now what would you do? How slow do you think you can make this? How fast do you think it is happening? If it is entirely due to molecular diffusion, no thermal currents, no gravity, no advection, no forced convection. Very slow is of course how slow is very slow. How does it go like a power of t? This is what you should ask. An initial distance, a little distance here, d at time 0 as compared to a distance d at time t, the question is how fast does d of t increase with t. We will make this very precise now, but how would you say it is happening in the case of diffusion? Well, diffusion is like a random walk. So it is like this molecule goes here and then it purposelessly moves around and then it does this and so on, and slowly things spread out. So if you are doing a random walk as opposed to a purposeful walk at constant speed, then in time n time steps, the distance I cover is proportional to n if I cover it at uniform velocity in a given direction. But if I merely do a random walk in this fashion and I walk around like this and I retrace my steps in all directions, then the mean end to end distance goes like square root of the time, square root of the number of steps. So this thing is mixing like d of t is increasing like t to the power half times d of 0. That is very slow, very slow. You have to wait 4 times as long to go twice as far. So it is very slow. On the other hand, you can increase the speed, you can give it ballistic motion, and that of course means you are moving at constant speed, and then it will become proportional to t. You can make it super diffusive, super ballistic, you can accelerate it, in which case it will go like t squared and so on and so forth. So you can start increasing things, but the big surprise is generically, typically in phase space, this mixing in most dynamical systems occurs exponentially fast, just zips apart. Initially we have to make this very precise, we make this concept precise, so the separation is exponentially fast. So typically this would not be the situation at all. Typically this would go like e to the power lambda t d of 0 with a positive lambda. Of course it can't keep doing that, because if the phase space is bounded, sooner or later things are going to come back. But the fact is, the initial separation, if it is exponentially fast, we have what is called exponential sensitivity to initial conditions. This means a small initial difference in the initial conditions can lead to an exponentially growing separation. Any initial error therefore would propagate exponentially fast. Any imprecision in specifying the initial condition would propagate exponentially fast, and this is what chaos means. This exponential sensitivity is very, very crucial. This is really the characteristic. Now how would you quantify it, and we will do that. So the next step after mixing is exponential instability. I call it an instability because it really is, things are moving out, flowing away from each other. Exponential instability on the average. By on the average I mean there could be regions of phase space where you have such behavior, but there could be other regions of phase space where you have regular behavior. So some initial conditions could remain on periodic trajectories, some could remain on quasi-periodic trajectories, others could become part of this exponentially sensitive region where initial conditions would separate out exponentially fast. And then you could have much worse situations where almost all initial conditions would lead to this kind of separation. So the amount of regularity that you have in this sea of chaos is getting smaller and smaller. So what starts out as islands of chaotic behavior in a sea of regularity, gradually as parameters change can become an islands of chaos in a sea of regularity, can become the other way about, islands of regularity in a sea of chaos could happen. So this is what is going to lead to chaos. So exponential global Now the definition of dynamical chaos, there are several definitions of it possible, and there is no real unique absolutely unambiguous definition, depends on what you would like to look at, but there is a reasonably agreed upon definition with some caveats which I am going to talk about, and that is the definition I will use. One thing we would like to understand immediately is that if you have an infinite phase space, the idea of an exponential instability is not very strange. Here is a very simple example. I have a one dimensional phase space, not even two, just a line. And I have this equation, x dot equal to x on the real axis. This displays exponential sensitivity in this sense, in the sense we have just mentioned, because what is the solution to it? This implies x of t is e to the t times x of 0. So on this x axis, which is your phase space, here is the point 0, and we know that in this case the point 0 is a critical point because that is where the x dot vanishes, and it is an unstable critical point because it says any x of 0 to the right of this point flows away in that direction, and anything to the left of it flows away in this direction. So it is a repeller. We also know that if you start with a point here and a point here, so this is x naught and this is x naught plus epsilon, after time t this x naught finds itself here, which is e to the t times x naught, but this same fellow finds himself here, which is x naught plus epsilon e to the power t. So the initial difference epsilon has now blown up to a difference which is epsilon e to the power t. In that sense, of course, you have exponential separation, but this is a very trivial statement. This problem is integrable, completely integrable, and this is not what we mean by chaos. This is happening because the phase space is infinite, because it is unbounded, but this is not what we are interested in. We are interested in situations where the phase space is bounded and you still have this exponential separation almost everywhere, and this is a little hard to conceive. It is like having a separatrix at every point, because we have seen lots of examples where if you have a hyperbolic point, if this is a hyperbolic point and this is the stable manifold and that is the unstable manifold, then we know that trajectories would look like this, and then you see on either side of the separatrix, if I start here or start here, you can see that these two have very different futures, and in that sense the separation is enormous. I mean, it could even be exponentially fast, but the fact is this is not sufficient to produce chaos again. But something like this is going to happen. You have a separatrix in the middle, but now imagine a situation where it is happening almost everywhere. What would that imply? What would that imply? How could you possibly have separatrices everywhere in phase space, almost everywhere? It is clear that if you have an unstable periodic orbit somewhere which is unstable, so that things to one side of it move in one direction, the other side move out in another direction, then this phenomenon can happen. That indeed if you have unstable, and I am going to demonstrate this, if you have unstable periodic motion, so that on that trajectory you have periodic motion on the periodic trajectory, but slightly to one side of it you have things flowing away and the other side of it you have things flowing away in another direction, then you can have this phenomenon of chaos. So I am going to write down the necessary conditions, what looks like necessary conditions, and then we will justify this using simple models. I also need to make precise the idea of exponential divergence, which I will do in a short while. So this brings us to when chaos can happen. It has got many names. It is called deterministic chaos, the reason being that the rules that you write down are deterministic. There is no actual noise, we have not put in any stochastic element or noise or anything explicitly. It is also called chaotic dynamics, it is also called dynamical chaos, and so on and so forth. We will just call it chaos. It happens when you have 1, a bounded phase space, 2, exponential sensitivity to initial conditions in a manner which I will quantify in a second. We are going to define a quantity like the lambda I talked about here. And 3, this seems to be necessary for chaos, the one that I am going to write down now. There is no rigorous proof that it is always the case, but I do not know of any instance when it is not there. So in that sense it seems to be absolutely essential. A dense set of unstable periodic orbits embedded in this phase space. Now once you have these 3 conditions met, then the system displays chaotic behavior. So let us take this systematically. First, what do I mean by exponential sensitivity to initial conditions? So let us do that. Let me define that here. Oh, I should mention, and I will come back to this, beyond this global exponential sensitivity you could actually have dynamics which can be put into one-to-one correspondence with random dynamics. So the dynamics, even though it is determined by, even though it is specified by deterministic law, could turn out to be such that the outcome is like tossing a coin, it is as random as a coin toss, also called a Bernoulli trial. So we will come to that and I will show you how very simple models can generate that kind of dynamics. Notice also that I have not made any distinction between, I have not said anything about whether this is Hamiltonian dynamics or dissipative dynamics, conservative or dissipative, it is completely general as it stands here. Hamiltonian systems also display chaos, but the route to chaos is very specific. Dissipative systems display routes to chaos, much more rich structure of routes to chaos, many more routes are possible, and a lot of study has been done on this, but Hamiltonian chaos is very complex. The way it originates is fairly complex, and we will try to look at some aspects of it. Okay. So first, this business of exponential sensitivity, what do I mean by that? Well, suppose here is a phase trajectory and here is another phase trajectory, and let us suppose that initially you start with a point x0 and another point y0 which is x0 plus epsilon, and x0 goes off in this fashion and y0 goes off in that fashion. I would like to ask, how is this separation increasing as a function of time? My suspicion is that it increases exponentially fast, and if so I would like to know what the exponent is. This is what we would like to do. If that is a suspicion, then let us call, we know that x0 minus y0 equal to epsilon, this is the difference between these two guys. Okay. I ask, what is x at time t minus y at time t? If this goes like e to the power lambda t times the initial distance, then it is clear that if I took this quantity and divided by x of 0 minus y of 0, this should go like e to the power lambda t, right. I would like to extract this lambda, so I take a log, then I get a lambda t. I would like to extract the lambda part, so I do a 1 over t of this, and I take the limit as t tends to infinity. Okay. What do you think will happen to this? What do you think this quantity will be if the phase space is bounded? You agree this is going to detect an e to the lambda t. I waited long enough, it has gone off. What do you think is going to happen if the phase space is bounded? Pardon me? It will end up as 0. The reason is x of t minus y of t can never become bigger than capital L, the size of the system, and then you have a 1 over t down here. So the moment you take this limit, you are going to end up with a 0. How would you avoid that 0? How would you avoid it? I would like to find out, by the way, what is this whole quantity going to depend on? It depends on the dynamics, it depends on how I specify x as a function of time, right. It depends on the rules of the game, the dynamical evolution equations. What else does it depend on? On the initial condition, it depends on where x0 is. It certainly depends on where x0 is, and I would like to have a property of x0. So I would like to call this whole thing lambda of x0. It exists, and this thing is called the Lyapunov exponent. Right. And it depends on x0, but now the way I have written it, it also depends on y0. I would like to get rid of that dependence on y0. So what should I do? Pardon me?
Y0 equal to x0 plus delta x.
And then what should I do to delta x? It is epsilon. I put an epsilon already. So what should I do? Epsilon tends to 0. Epsilon should tend to 0. So I should take a limit epsilon tends to 0, where x0 minus y0 equal to epsilon, and I would like to let epsilon tend to 0. So do you think this would do the trick?
Because limits are evaluated on inside of.
Yeah, so what should I do? What do you think will be the answer here?
0.
Will be 0. So to get a non-trivial answer, what should I do? Change the order of limits. Change the order of limits. This is crucial. So change the order of limits. So limit epsilon goes to 0, limit t tends to infinity will indeed do the trick. That will indeed do the trick. This is a little bit like saying if I have a to the power b and I am going to let a and b both go to 0 from the positive side, the answer depends on which one you let go to 0 first. If you let b go to 0 first, the answer is 1, but if you let a go to 0 first, then the answer is 0, right. So the order of limits matters, and of course mathematics will not tell you what the physical situation is, it is not going to tell you which order you should choose. It is the physics or whatever you want to derive, whatever you want to understand, that is going to dictate what order you prescribe, and this is the definition. This is the definition of the Lyapunov exponent. Yeah.
So if difference between x of t and y of t is going up exponentially, why do you need to take the limit t tends to infinity? Just divide 1 over t directly get the lambda.
I'd first like to find out what is happening on the, let me explain this a little bit. We would like to find out what is happening to this initial point. So this initial point is on some trajectory, right. So a small initial error here, this trajectory would move like that and this would move off in this fashion. What I'd like to find out eventually is what's the Lyapunov exponent on this trajectory. So once this initial separation becomes this much, I'd like to reset the clock here, and then this guy goes off like that, this fellow goes off in this fashion, and I'd like to find out what the separation is, etc. So each time I'm going to actually reset back to the trajectory that I'm interested in or the region of phase space I'm interested in and find a property of a region or a particular point. Okay. Now of course if you do this for a finite amount of time, you don't get a limit at all. Okay. So it's not going to give you the definition of e to the power lambda t. The statement I am making is precisely in the same spirit in which I said that the flow is like e to the power lambda t. When you linearize a flow, it is e to the lambda t, it depends on the linear matrix and depends on the eigenvalues, whether they have got positive real parts or negative real parts will determine the stability, but these are asymptotic statements. Of course after some time the system is no longer linear, it goes out, but the whole idea is to take a limit inside a region always. I am not saying this very clearly, but I will give examples as we go along. I realize it is a little hazy at the moment, but let me give an example as we go along. You need this limit, but you have to be careful that the limit, this limit is taken before that limit, because in the other direction it just gives you 0 and does not tell you anything about separation at all. Okay. Now let us ask, suppose the separation is like the square root of t, like it was in the case of the diffusive motion we looked at, then what would the Lyapunov exponent be? What would it be? Suppose it goes like square root of t. So this over this goes like t to the power half, and then of course you realize that you get a half outside and you get 1 over t log t, and what happens to that? It goes to 0 because log does not increase as fast as the power t. Suppose it goes like t to the power a million, what happens then? It is still the same, it is still the same. So you see this test, this definition will distinguish between things which have exponential sensitivity as opposed to any kind of power law sensitivity. It does not matter at all. No matter how high the power, you will still not find a positive Lyapunov exponent. On the other hand, the moment it is exponential, you find this. Now I could ask the following question, suppose the separation increases like t squared, e to the power t squared, what would happen? What would happen to this? It would become infinite. So this is super exponential, it is faster than exponential, but you see we have seen in our experience of dynamical systems that generically it is always, unless you have singular points, strange kinds of behavior, generically it is always exponential. We saw that when we linearized the matrix near critical points that you always had exponential behavior because you have the Jacobian matrix and then you expand and the solutions are exponentials. So the typical case is in fact exponential always. The only question is it 0 or non-zero? If it's, is it positive or is it negative? If it's negative, of course you have shrinkage, no growth at all. Is it 0, in which case you do not have chaos, or is it positive, in which case you have chaos. Now the next question you should ask is, look, all this is nice in one dimension, but really I have an n dimensional phase space in general. Then the question is, in which direction should I choose the epsilon? And there is no reason why if I start here and I start with a neighboring point here, this separation can grow at one rate, but that separation can go at another rate. Therefore in n dimensional phase space, how many possible Lyapunov exponents could you have? N of them, corresponding to n directions. So really you have a whole Lyapunov spectrum, and if I define the distance between 2 points by the Pythagoras theorem or something like that, then what I am getting by this definition will be the maximal Lyapunov exponent. Obviously if some directions come together and some directions grow, it will only the growth that will matter, right? Because take this, suppose you start with initial points in this circle, and these points, let us say after some time, become like this. They occupy, maybe the volume is the same, or even the volume shrinks, you do not care, they occupy a space like that. Then this point could go there, this point could come here, but you see any separation in this direction has shrunk to practically nothing, but a separation in this direction has increased to this. When you compute this distance here between these 2 points, it is only the increased dimension that will dominate, and the other direction will not dominate at all. So you would really find the maximal Lyapunov exponent. And this also tells you that if there is shrinkage of phase space volume, if there is dissipation such that an area becomes a line after enough time, or a higher dimensional volume becomes a lower dimensional object, it still does not matter because you still lost information. So this error has grown exponentially, even though the error in this direction has shrunk maybe even to 0, it does not matter, but the initial error has grown, and this is what the Lyapunov exponent is guaranteed to do. So having said this, we need now to have some systematic way of understanding this whole business, and we need a simple model. Like we had the harmonic oscillator in the case of integrable systems, we need a harmonic oscillator for chaos. Unfortunately there is no such simple model, and the reason is simple. The reason is, if you have differentiable dynamics, if you have dynamics described by differential equations, set of differential equations, then in one dimension there is nothing to solve. You have x dot equal to f of x, you can always solve this in principle. In 2 dimensions we have nonlinear systems which would look like x1 dot is some f1 of x1 x2, and x2 dot is f2 of x1 x2, and your phase space is a plane x1 x2, then you cannot have chaos in this problem at all, because the only kinds of critical points you can have here would be where the right hand side vanishes, and there would be isolated critical points, and we have classified the simple critical points. There is one more possibility which we did not look at, and that is what is called a limit cycle. It could so happen, and does not happen in Hamiltonian systems, in dissipative systems it could so happen that you have an isolated periodic trajectory, a single isolated periodic trajectory, such that you may have a trajectory like this which is periodic, such that there could be, for example, an unstable spiral point here, and things could go and flow into this as time permits, as time increases. So this is a stable periodic trajectory, and wherever you start it is possible you may flow into this given enough time. Then an isolated periodic trajectory of this kind is called a limit cycle, and it is a hard problem to discover limit cycles. You generally have to do this numerically. I will give some simple examples where you can actually work it out explicitly. But this is possible, this kind of attractor is possible, and it is the next in the hierarchy of attractors. The first one we had was attracting fixed points or critical points, and the next one is going to be limit cycles, stable limit cycles, and after that there is just nothing in a plane, that is it. But if you have 3 or more variables in 3-dimensional space, it is possible for the phase trajectory to wander around forever and ever in a region like a ball of wool, never intersecting itself, but not periodic, not leaving that region either. In 2 dimensions that is not possible at all. You can't have big tangles because anything that comes in, if it can't intersect itself, it has to fall in or else become part of a periodic trajectory. But in 3 dimensions you can see that the trajectory can go around like a ball of wool. So it is exceedingly complicated, very strange peculiar object called a strange attractor, does not intersect itself, not periodic motion, not quasi periodic motion, but does not leave that region either, and in that region called the attractor, 2 initial points that you start with would exponentially separate. Okay. So this is possible when you have a third variable here, but then we do not have any very simple analytic solutions. Such systems will not have analytic solutions, and therefore except numerically I can't illustrate this to you. And all of you by now have seen this famous icon of chaotic dynamics, the butterfly, the Lorentz butterfly, which is available on all kinds of websites, where if you run this for a long enough time you see the solution to this differential equation just moves around in a completely chaotic manner in a very strange fractal object called a strange attractor, but there is no way you can write down explicit solutions. So in that sense it is difficult to understand except numerically. What we would like to do is to understand it in an analytic fashion, in at least a semi-analytic fashion, and here is where discrete time dynamics comes in. It turns out that while in the case of differential equations you need at least 3 variables coupled non-linearly, they must be non-linear in order to have chaos possible at all. If the dynamics is not differential dynamics, namely it is not differential equations but difference equations, then even 1 variable is sufficient. So this is the big advantage you have simple models possible with just 1 variable, a scalar variable which you can write down, generally a variable, a number between 0 and 1, such that there is a prescribed rule by which this number changes from time step to time step but in discrete time steps, and then I can produce chaos for this, and such objects are called maps. So let me write that down. For continuous time is the minimum n equal to 1 will do, and instead of calling them differential equations we call them difference equations, and just as we call differential equations flows, difference equations are called maps. So let me focus on maps from now on, and I have a single variable and a variable I call x, a real number, and what is the map? It says x sub n equal to some function x sub n plus 1 of xn so this is called a 1-dimensional map. That is my rule, that is my dynamics. Of course it is not real life, it is just a very simple model, a sort of caricature of what happens, but in a sense you can actually map very physical problems to it. For instance, the insect population each year or each season would depend on the population of the previous season in a certain nonlinear fashion, and that would be an example of this kind of map. In fact such maps were first studied in the ecological context, and they realized, in particular several people did this, the history of chaos is very interesting. Lorentz, E.N. Lorentz, I should write this, Lorentz. So we will assume this variable, this thing is real, and let us ask what happens if I look at the very simplest of maps, a linear map. So let us put xn plus 1 equal to axn, where a is a real number, positive number say, and I specify x naught is an element of the real numbers. What happens to this map? So on the x axis I start with some point x naught, and then I find out what's x1, and then I find what's x2, and so on. How would you do this? The solution is utterly trivial, right? I mean, x1 equal to a times x naught, x2 equal to a squared x naught, and so on and so forth. So how would you do this numerically? Do this by this method of successive approximations, isn't it? So what you do in general is plot the 45-degree line and you plot this function y equal to ax. Let us suppose the slope of this function is less than 1. So this is and I start with an x naught here. Then graphically how do I find x1? This is called the method of successive approximations, right? So what you do is to go to this point, right, and then go horizontally to this 45-degree line, call that x1, and then you go to this point here, call that x2, and so on. And what's going to happen wherever you start? You're going to flow into this origin, right? Now what would you call this origin? It's not a critical point, there is no differential involved here. What would you call it? What would you call a point for which it turns out that xn plus 1 is equal to f of xn itself, equal to xn itself? So this means x is equal to f of x. These are the fixed points, right? These points don't change, because if you under iteration under this map it does not change at all, and they are called the fixed points. So for maps, fixed points would play the same role as critical points played in the case of differentiable dynamics. So for this linear map y equal to ax, the fixed point is the solution of x equal to ax, which is x equal to 0. Is it stable or unstable? It is of course stable. You can see that the thing comes in. If I started here, for example, the next step I would go here, then I would go here, and then I would go here, and I would flow into this point here. So since I flow into this point from both sides, x equal to 0 is a stable fixed point. Is this true for all values of a? If a is greater than 1, what do you think is going to happen? You would flow away from it, right? So it is clear that if I had a greater than 1, I do just the opposite. And a greater than 1 would be something like this. If I start with an x naught, then I go to this point, call that x1, this is x1, and then I go to this point, so this is x naught, this is x1, and then I go off here to x2 and so on, and it is clear I flow away from this critical point. What happens if a is exactly equal to 1? Then it says the map is x equal to x, that is the identity map, and that is a degenerate case, because then every point is a fixed point. Wherever you are, you do not move at all. It is a completely degenerate case. So it is a trivial degenerate case, and it is clear that everything is going to depend on what this f of x does in the vicinity of a fixed point. Let us look at a slightly more complicated case. What happens if I have a map which looks like this? Say that is my map. What is going to happen? There are two fixed points, there is one here and there is one here. So if I start at any point here, I go here, find the solution, and I flow into this. So wherever I start, if I start here, I find this, and I am into this. If I start arbitrarily close to this, I am going to flow away from it, and if I start arbitrarily close to this, I am going to flow into it. Any region, any point in between these two places, these two fixed points, if I start, I am going to flow into this. This would therefore be a stable fixed point, and that would be an unstable fixed point. And of course you can see that they must alternate, and it is also clear that this is unstable because the slope at this point is bigger than 1, and this is stable because the slope of the map at this point is less than 1. So that is a simple criterion for whether a fixed point is stable or unstable. So if x star is a fixed point, then f prime of x star greater than 1 implies x star is unstable, less than 1 implies x star stable. By the way, there is nothing which says that the slope can't be negative. That is certainly possible, because you can easily see that if the map were a function like this, then too it would flow away if the slope is greater than 1. On the other hand, if the map is like this, it would flow into it. So it is not f prime of x star that is important, but the magnitude of it is important. So you need this. What happens if the magnitude is exactly equal to 1? What would happen? If it is plus 1, it would be the same, but if it is minus 1, it would go in a loop around it. So all those of you who have studied the method of successive approximations, which is all I am doing here, because what am I doing? I am each time trying to find the roots of the equation x equal to f of x by taking a trial solution, finding f of x, calling it the new x, find f of x, call it the new x, and keep doing this to see if I converge or not. And whenever there is a stable fixed point, it is going to converge to it, provided you start in the right basin of attraction of this point. So you could have, for example, if this were slope minus 1, exactly of that kind, then if you start at some point, you would go here, you would go here, you would go here, you would go back, and you keep doing this loop here if the slope is exactly minus 1. So you would neither go in nor go out in that case, and such a thing is called an indifferent fixed point, a marginal fixed point. What would happen if you had a map which did this? At some point there is a tangency. What would go on now? That is a fixed point, because that is where the map intersects the 45-degree bisector, but now the slope is exactly 1 at that point. Would you call this stable or unstable? What would you call it? Well, it depends. If I start here from the left, from below the slope is less than 1, and from above it is greater than 1. So it is clear that if you start somewhere here, you would just flow off. But if you start here, you are going to flow in. So you have stability from one side and instability from the other. So it is really unstable in that case. This sort of thing is called a marginal fixed point or an indifferent fixed point. And what can happen even better is the following, and this happens quite often. If you had a thing like this, a fixed point is missed out there, and let us say the slope is really bigger than 1 elsewhere, and then it is chaotic in some fashion. What can happen now is that if you find yourself in the vicinity of this region, then once you are here, you do this, and then you would flow off, and you can do this for an arbitrarily long time if you are closer and closer to that point, which means for a long time you would think that the system is regular, but it really isn't. It is chaotic, it moves off, and then if the dynamics is such that the map brings you back to the vicinity of this point, of this little tunnel region, then you would again spend a long time imagining that the system is regular, and this is called intermittency. It is really chaotic, not periodic, but there are apparently long periods or bursts of regularity followed by bursts of irregularity and so on. A very classic system. This is only one route to intermittency, there are many other, this is just a mathematical model. The dripping of a faucet, a leaky tap, very often intermittent, because if you watch it long enough you see the drops building and then it falls, a very complex problem, it is a classic chaotic problem, because the surface tension, the gravity, the viscosity, everything plays a role, and this falls and you think it is falling in a regular way, but actually it is not falling regularly, it may fall regularly for an hour, and after that you find there is several drops at the same time, and then very slow, again very periodic and so on. So it really goes into intermittency in this fashion. Now these simple models can actually be used to mimic much more complicated situations, and what I am going to do next time, tomorrow that is, I am going to start with a simple one dimensional map and show you how you have full blown chaos in this problem, and then we will look at a system which has a whole root to a period by doubling root to chaos. So it will give us some handle on how to compute Lyapunov exponents and so on. So we will do that tomorrow.